All right. Greetings, Saintsmen. We're going to go ahead and get started with lesson 10.1, which is on uh, the circles, is what chapter 10 is going to be on. So we're going to talk about the various parts of a circle. First thing that you guys are going to need, well, I can just click on auto shapes. And when I draw a circle here, it's just going to automatically fix it. You guys are going to need to get a your compass, all right? So make sure that you go, oh, it even fixed me circling compass there. Um, Now, I'm going to start to name all the various parts of the circle. The first one, I swear to you, is kind of a silly name for it because it's so obvious. But this is literally what's called the center of the circle. So, as we define these things, now if we take a line segment, oops, it's difficult for me to make this line segment here because you'll want to have a straight edge. I don't have one here to put against my computer screen. But I make this line segment and it goes through the center, okay? And that's going to be a special type of line. Now I'm going to make another line segment not through the center, okay? In fact, let's not make these parallel. Let's go ahead and make one like this. Now, anytime I have a line segment that ends on the circle, so these points like this right here is on the circle, this is what is going to be called, and this segment is what's called a chord. Oops. Oh gosh, this is what I sometimes get frustrated with the outer shapes. And a chord, by definition, is a line segment. And it, with both endpoints on the circle. So the question is this line right here that I made, this line segment, also a chord by definition? And yes, it is. Now, specifically, it's what's called a diameter, which is something we talked about actually a little bit in the last chapter, especially when we were doing the fire pit problem. And this is a chord, right? Diameter is specifically a chord, not just a line segment, but a chord is a line segment. And it's a chord through the center. So diameter is a type of chord. Now, we also could have an endpoint at the center and then on the circle. And this is what is called a radius. And you guys already know all radii are going to be equal because it's from the center to the circle to the point on the circle is all equidistant. So this is a line segment with one endpoint on the circle and the other at the center. Right. So this is all really important stuff because as you guys have seen when we have been doing this course, that we have all these really particular definitions. Okay, so let's go ahead and use this information. I'm going to, again, have my version of the compass is where the software just fixes the circle for me. Okay, and I want you guys to copy down the following diagram. So I have here this point. Oops. Some chords I'm going to draw here. Here's a chord here. Here's a chord here. And here's a chord here. And then we're going to do one more chord from here to here. Let's name these guys. This guy is point A, B, C, D, E, and then F. So, how do we name this, right? Remember how we named polygons, where we would name it by the vertices? Now, think about this. How many vertices do we have here? And like for a triangle, there's going to be three vertices, right? Because there's three sides. For quadrilateral, there's four. But while you guys might count five here, how many could I prospectively put on this entire figure? And it's the answer is infinity, right? So I'm going to name instead, a circle gets named by its center. So this guy literally is circle E. You guys can even write, you can write circle E, but this little circle with the dot in it, that it suffices for a circle. Now let's name all of the radii for circle E, plural for radius, and we're going to name all the chords for circle E, and we're also going to name the diameters for circle E. Now all the radii. So it goes from the center to a point on the circle. So from the center E would go to B, so line segment EB. E would go to A. E would go to F. That's drawn, and also E goes to C. Now I could draw one between E and D, but it hasn't been drawn here. So it's like naming something that's unnamed. It's kind of something we could make, but we don't need to. The chords here. We would have the anything that's going to go from a point, right? And point on the circle line segment with another one on the circle. So we have AB. We'd have AD. We'd have BF. And of course, we'd have AC. All right. So what else do we have? Well, we're looking for diameters. So diameters, we're only shopping from these segments right here. Is AB a diameter? Well, no, it doesn't go through the center. Is AD? No, it doesn't go through the center. Only BF and AC, all right, go through the center. So those are specifically that. Okay. Some more vocabulary for you guys, all right? That's why it really is important for you guys not to rush through these because we're going to get to class. I'm going to start to ask you guys these questions in the directions, and then there'll be these questions about like, oh, well, what is that? Well, that was the lesson, big guy. All right. So let's draw a circle here. And I'm going to draw a couple of lines as they relate to this circle. And here's the relationships we have. We have a line going through the circle. Oh man, this one's going to be tough for me to draw with the computer. Let's see. Doing my best. Okay. So here I have this circle. Let's name it. He deserves a name. So we give him a center and it's point Y. Now, this line that intersects at 2 places, this line is what's called a secant geometrically, right? With regard to the circle. And it's just a line that intersects a circle at 2 points. Now, what's possible? We can intersect it at 2 points, right? We could do it at just 1 point, right? Exactly 1 point. And this line is what's called a tangent. So this line is tangent to the circle, all right? And this is the point of tangency. Shows there's a special relationship there, okay? And a tangent line with regard to the circle intersects a circle at 1 point. What's the other? Possibility. Impossible for it to intersect at 3 points because it's no longer a line. And we could do it at 2, we could at 1, and we could also do it at 0. All right? Just do some various intersecting circles. This will be fun. If I make circles intersect each other, which they can, okay? Circles would do this. Like I could do a circle here and I could do a circle here. These guys, when we have intersecting circles, there's a couple ways we do it. This one has 2 points of intersection, right? Here and here, right? Or another fun way to do it, right? There's if we could make them intersect or circles intersect once, watch. I could do this guy, and I could do one interior. Oh man. So I'm gonna do this. I'm gonna move this guy. There you go. Boom. Look at that. That right there is my singular point of intersection, right? Or I could do like this. Circle here, circle here, right? Just like that. Boom. And we have one point of intersection. All right. And okay. This is what we call the common tangent. Okay. And it's that point of tangency. Okay. And these two circles are what we would call tangent circles. So anytime we have that singular intersection. Okay. Now, fun fact, we're going to learn, and then we have some other ones, right? So there's a few ways that we could do it with 0 for the record. Let's do this, okay? I'm still doing auto shapes, cool. So here are the ways we could do 0 with 2 circles. I could have a circle, and I could have another circle just inside of it. Or I have a circle, that's ellipse. Circle, circle, so many good. So like, oh, it's an oval. No, no, no. That's 0 points of intersection. And here's actually a fun one right here. I could do this guy, and I could do another one inside of it. Oh, this one didn't turn out that great. But here's what makes these ones special. I can get it to snap to. Oh, goodness. It's tricky. Ah, there we go. Now, this one is fun. This guy shares the same center, and this is what we call concentric circles. Cone center, concentric, with the same center. Concentric circle. And of course, these ones have 0 points of intersection. Okay. So let's get back to tangency. Drawing another diagram here. Okay. And I'm going to draw a line. A tangent line. Man, that's a really bad tangent line, guys. I'm sorry. Let's see if we can draw one up and down that's a little bit better. Oh, yeah. There we go. That vertical line. Is it easier for me to position my hand so it goes vertically? And here we go. This is circle P. All right. Now, circle P has this point T. Okay. And point T is on line L. Okay. And circle P is the point of tangency T. Okay. And then here's what's known is that from the point of tangency to the center of the circle, okay, that radius is perpendicular. Guys, I called it circle P, and I think I erased the P at some point. Here we go, circle P. Sorry. That or else I named it, but then I never wrote the middle here. Okay, the center. So Um, the relationship of the point of tangency to the center of the circle for the line that is tangent is perpendicular. So PT is a perpendicular line to line L. Okay? So that radius is perpendicular. More fun facts. Some more fun relationships. Let's go auto shape. Let's get another circle P. All right. Gosh. So we have 2 points of tangency here. So this radius PB and another one here. We have PA. Okay, and then these guys go to this point C right here. Okay. Um, lines that are tangent and intersect, okay, outside of the circle, as long as these guys are going to wind up being congruent. Okay, so this BC and AC are congruent segments. All right, as long as C is tangent, and it'll have 2 points of tangency to any circle. So any point outside of a circle has 2 tangent lines, right? That will have congruent distances. Right. So I've got 3 numerical examples for you guys. All right, let's try it out. And it's this. I have P, I have T, and then I have this point S outside the circle. All right. And I have the following distances. Now, guys, unless you are told that a relationship exists, we'd have to prove that it exists, right? Unless it's given. Well, here's all that's given to us are these distances. We have 24 for the radius. We have 44 for this line TS that appears to be tangent, but that's not given. And then we have here this segment PS, which is 51. Okay. All right. Now you can't ask me like, oh, Granados is 51 referring to just this part. Well, no, it would have to be the same as that. That would be 24. So PS is 51. The question is TS tangent to circle P? All right. Now, if it were tangent, if then what type of angle would this be, right? That would be perpendicular, which means that this would be a right triangle, meaning that the Pythagorean theorem would apply. So we can apply the Pythagorean converse and test, and then actually check these values. 24 squared plus 44 squared equaling 51 squared. All right, and that's the question. Is that really the case? Okay. So let's try it. 24 squared. Again, let me go to our calculator. Okay. Let me go to my Texas Instruments account, right? Oh, goodness. There we go. A little bit of a flex there, guys. I just click sign in for me. Boom. I'm a calculator. And get my 24 squared. So that's 576. Plus 44 squared. This is 1936. And 51 squared, which is 2601. So when we add 576 and 1936, we see that that is 2512, which is not equal to 2601. So the answer simply is no. It's a simple one word answer. All right. So, new problem. The outer shape working. Circle A. B. And C. And here's what we're given. We're given that this segment BC is 36, and the segment out here is 24. Now people are like, well, does this apply here to the entire line or just this outside segment? Now, gentlemen, you'd have to explain to me, right, how this would have to be, this would be a right triangle as long as we have the following, which is B is a point of tangency to circle A. So we're going to find the radius. Now, again, if that's the case, guys, remember, I need to find this segment, which would have to be the same as this one because, and it's impossible for this one to be 24 because this would be the hypotenuse, which would have to be the longest segment of the circle, the longest side, which would have to be bigger than 36. So we can just use the Pythagorean theorem here, knowing that AB squared plus BC squared, right? These two legs can be equal to AC squared. Now, how do we create each of these? Well, we're going to do it through segment addition. AB is merely R, so R squared. BC is 36 squared, but AC is equal to R plus 24 squared. All right. So we have a little bit of algebra to do here. All right. All we knows. So R squared is still R squared. Uh-oh. Pen died. It keeps doing this. 36 is 1296 equal to R plus 24 times R plus 24, which we're going to have to remember to FOIL the first, outer, inner, and last. So R squared plus 1296 is equal to our target R is R squared, 24R, and 24R, which is going to be 48R, and then 24 times 24, which is going to be 576. All right. So we have R squared plus 1296 is equal to R squared plus 20, is 48R plus 576. Now, I could subtract R squared from this side, and I do that from the other side, it's going to cancel out both of these. So what I'm left with now is 1296 is equal to 48R plus 576. And then, of course, my next step is going to subtract 576 from both sides. It's going to cancel on the right. 1296 minus 576. Oops. 720. And then, of course, I'm going to take 720, divide by 48. That's going to be 15 is my radius. All right. Awesome. All right. Last problem for today is going to be a quick one. Have my circle L. This is H. This is K. And here are my quick things. Oh, sorry. A J out here. JH is equal to 7x minus 23. KJ is equal to 61. And given that JH is tangent to circle L at H, and JK is tangent to circle L at K, okay, and solve for X. Fellas, it's a pretty straightforward one, right? Because what do we know about this segment and this segment then? They're going to be congruent, okay? HJ is congruent to JK. So 7x minus 23 is equal to 61. 23 to both sides. 7x is going to be equal to 84 divided by 7 on both sides. 7 factors out, and x is equal to 12. All right. Thank you, Saintsman. Good luck. If you have questions for me, please reach out.